So why does it tend to get smaller as we get left to right? So if we look at it, I mean, common sense would say it would get bigger, right? So we add, okay, if we just, let's say we're just going across group 2. As we go from lithium to beryllium, we add protons, neutrons, and electrons. We add more stuff. Go to boron, we add more protons, neutrons, electrons. We add more protons, neutrons, electrons. So we keep adding protons, neutrons, and electrons as we go across the table. So you would think that the atom is going to get bigger, but it does the exact opposite. Okay, instead of getting bigger mostly as we come across, it actually gets smaller most of the time. And the question is why? Why does it get smaller as we go left to right? Well, it's got to do with an attractive force. So remember, as we move left to right, our Z effective increased. Okay. So if we look back, when we calculated it, when we were going across, here, where is it? This is for group 3, but our effective nuclear charge kept getting bigger and bigger and bigger and bigger. Right, so those valence electrons were feeling a stronger and stronger and stronger and stronger effective nuclear charge. Okay. Now, remember the other big thing is distance. But as we're going across the periodic table, all of the electrons are going in the same principal energy level. So the distance isn't changing. Okay, the only thing that's changing is our nuclear charge. All right, that effective nuclear charge is going up. All right, so these electrons are staying the same distance. The charge difference is increasing, so what happens is it pulls all these electrons in, and the atoms get smaller. Okay, so as our Z effective increases, and the electrons are in the same PEL, the electrons are pulled closer to the nucleus. Okay, and our atomic radius decreases. Our atomic radius decreases. Now, this is for atomic radius. All right, these are for atoms. It's a little bit different for ions. Come on, flip over. So let's talk about ionic radius. What happens with our ions? So our ionic radius, really the size depends on nuclear charge, number of electrons, and where valence electrons are found. So let's deal with the formation of cations first. So let's say we're going from Na to Na plus 1. All right. When we're forming cations, they're always smaller than the parent atom. And there are really two different ways that they get smaller. All right, so let's look at sodium first. All right, so sodium has 11 protons, 12 neutrons, it's got 2 in the first, 8 in the second, and 1 in the third. Now, here's a question for you. Ready? Okay, when this goes from Na to Na plus 1, this electron right here is lost. When this electron is lost, this whole principal energy level is gone. If this whole principal energy level is gone, okay, what's going to happen to the size of this cation? Well, it's going to decrease. All right, so the number of principal energy levels decreases. So the ion is smaller. All right. So that's just common sense. All right. If we lose a whole principal energy level when it goes from an atom to an ion, all right, this whole thing is gone. So the size of the ion is going to be much smaller than the size of sodium. Well, what if we do this? What if we have Mg going to Mg plus 1? No, it's not going to do that. Okay, it's not going to do that. We know that. It's going to be plus 2. But let's just say if. All right? So, if that's the case, we've got 12 protons, 12 neutrons. Okay. We've got 2 in the first, 8 in the second, 3, 4, 5, 6, 7, 8. And then with Mg we have 2. And we're going to lose just one of them. Okay, this one's lost. Okay, this is still going to be smaller. Okay, the Mg plus 1 is going to be smaller than the Mg. The question is why? Okay, why does this get smaller? Because we're not losing a principal energy level anymore. All right, but what happens, okay, remember all these electrons are repelling each other. This one has 2 electrons right now when it's just Mg, and these 2 electrons are being repelled by these inner electrons. When we lose one of them, that repulsive force decreases because we go from 2 electrons in the outer principal energy level to only 1. All right, and because that repulsion decreases, all right, if the repulsion decreases, the atom is going to get a little bit smaller. So my electron repulsion is reduced, so the ion becomes smaller. Right? So that's what's going on when we're forming our cations. What happens with anions? Well, when we form anions, they are always bigger than the parent atom. So, I don't know, let's look at fluorine. When fluorine becomes an anion, it's going to gain 1 electron. It becomes F plus 1. Oh, not plus 1, F minus 1. So, usually it has 9 protons and 10 neutrons. It's got 2 in the first. Oops, 2 in the first, not 3. 9 protons, 10 neutrons. 2 in the first, and 7 in the second. 2, 3, 4, 5, 6, 7. All right, now we know that it wants 8 valence electrons, so it's going to gain an electron. Okay, and here it comes. All right, so it's going to gain an electron. And this gets bigger. The question is why? Why does it get bigger? It's going in the same principal energy level. why is the ion bigger than the atom? Well, we're increasing the number of electrons in this outer principal energy level. This increases the number of electron-electron repulsions, which causes the electrons to spread out and the ion gets bigger. So when we add this electron, it increases the number of repulsions between the inner electrons and the outer ones. So there are more repulsions going on, okay? And because of that, these outer electrons get to spread out, so it gets bigger, right? Now, that's true for all the anions, okay? That's why all of our anions get bigger. Now, let's talk about isoelectric series. These are groups of ions that have the same number of electrons. So we're dealing with these isoelectric series. The size depends on the nuclear charge. So let's look at an isoelectric series. O minus 2, okay, it would have 10 electrons. F minus 1 would have 10 electrons. Na plus 1 also has 10 electrons. Mg plus 2 has 10. Al plus 3 has 10. They all have the same electron configuration. 2 in the first, 8 in the second. Right? But I can put them in order of atomic radius, but it's dependent on our nuclear charge. So if we look at this one, this has 8 protons. This one has 9 protons. This one has 11 protons, this one has 12 protons, and this one has 13 protons. Okay? The effective charge, effective nuclear charge, okay, is going to be the same for all of them. Right? So the bigger the charge, the bigger the nuclear charge, the more it's going to pull them in. So the size gets smaller as nuclear charge increases. Okay. So in this case, the aluminum would be the smallest and the oxygen would be the biggest when we look at these isoelectric series. Right? And it's based on nuclear charge. All right. Do I want to keep going? wanted to do ionization energy, so we'll do that and that. All right, let's keep going. So let's talk about ionization energy next. And our ionization energy is the amount of energy needed to remove an electron from the ground state of an isolated gaseous EOUS atom or ion. Okay, so we're removing electrons. How much energy we actually have to add to the atom or ion to remove the most loosely bound electron is what we generally say. All right, so the first ionization energy is the amount of energy to remove the first electron. The second ionization energy is the amount of energy to remove the second electron. Third ionization energy, fourth ionization energy, you can keep going. Okay? So ionization energy of an element increase as you remove electrons. So if we look at how do I want to do this? Let's look at Mg. All right, and it's, if we look at its electron configuration, it's 1s2, oops, 1s2, 2s2, 2p6, 3s2. All right, so in these, okay, the most loosely bound electrons is out here in these 3s. Okay, so our first ionization energy or to remove one of these 3s orbitals is 738 kilojoules per mole. Okay, so we would have to add that. All right, so the next electron, the second ionization energy, is 1,451 kilojoules per mole. So that would be removing the second electron, or the second 3s. But look what happens when we go to the third ionization energy. It jumps up to 7,733 kilojoules per mole. Why is it so much more? Well, now we're pulling out of here. Okay. Remember, okay, we're talking about a force of attraction. Right? So these are much further away than these. All right, so these are going to be a lot easier to lose than these inner electrons. All right, so you can see that our numbers are going up. So let's write this. There is a huge increase when you start removing core electrons. Okay, so this is a core electron. These are core electrons, so that energy to remove it is much, 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 much higher. Now, in general, smaller atoms have higher ionization energies. It really depends on the effective nuclear charge and the distance from the nucleus. Okay, so that ionization energy is dependent on, that attractive force between the outer electrons and how far they are from the nucleus. So if we go left to right across the period, okay, so we're going across the period, okay, coming from here to here. Okay, our ionization energy in general is going to increase. So over here, our alkali metals, our ionization energy is the lowest. And over here, it's the highest. Why? Okay, what's happening? Why is ionization energy increasing as we go across? Well, remember, our effective nuclear charge is increasing. Okay. So as we go across, our nuclear charge is increasing. This is causing the distance between valence electrons and the nucleus to decrease. So let's think about this. What's happening to our attractive force then? If our effective nuclear charge is increasing, so it's getting bigger, and the electrons are closer to the nucleus, our attractive force is going to be much, much higher, much stronger. If the attractive force is much stronger, it takes more energy to remove. So our ionization energy will increase. So if we go across group 1, okay, remember this would be the biggest of group 1. This one would be the smallest, right? So this one's going to have the strongest force of attraction between the outer electrons and the nucleus. It's going to take the most energy to remove an electron from there because of that effective nuclear charge, okay, and the distance between. This has got the stronger forces. Now, there are some irregularities as we go left to right. So, for example, as we go from beryllium to boron, The first ionization energy for beryllium is 899. Okay. We said as we go across, generally the ionization energy increases. But if we go from beryllium to boron, it goes from 899 to 801. It actually goes down. The question is why? Okay, why? Well, if we look at electron configurations, this one is 1s2, 2s2. Okay. For boron, it's 1s2, 2s2, 2p1. Okay. So in this case, we're losing a 2s. And in this case, in boron, we're going to lose a 2p. Well, we know that this is going to be more stable than having one 2p electron. All right, so it's going to take less energy to actually remove it than this. All right, so there are some exceptions. All right. Another one, going from nitrogen to oxygen. First ionization energy for nitrogen is 1402. For oxygen, it drops down to 1314. The question is why? Well, if we look at their electron configurations, we got 1s2, 2s2, 2p3, and then this one is 1s2, 2s2, 2p4. Okay. If we look at that 2p, this would be up, 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 but this one would be up, 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 down. Remember when we talked about orbital notation and we said half-filled orbitals tend to be stable? That's what's happening here. Right? So this is a half-filled p orbital. Up, 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 up. This has got this extra one. It's going to be easier for this to remove because of that. All right, so you get this irregularity, right, depending on your orbitals as we go across. And I think I have a, let's see here. I do. So this is a chart of ionization energy, and I will actually post this. All right, and it kind of makes, and it shows us what's happening with ionization energies in the periods. All right, so period 1, hydrogen is here. Okay, we go to the right, helium is higher. That makes sense. All right. Period 2, here's lithium. Beryllium is higher, but then it comes down. All right, and that's when we're going into the p orbitals. Up, up. Okay, so we got the second p orbital. Okay, then the third p orbital. Then it comes down for oxygen, but then it goes back up. All right, but in general, as we go left to right, it increases. Right, same thing's going to happen in period 3. We start low. Okay, here's Mg, then it drops back down for aluminum. All right, then silicon and phosphorus, it drops back down for sulfur, chlorine, and argon. It's following the same pattern. All right, and then we get into period 3. All right, and the same idea is happening in period 3. Okay, we get those irregularities based on your orbital notation. All right. Well, how about top to bottom? Well, here's a chart of some first ionization energy. What happens top to bottom? It's getting less and less and less, 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 and there actually aren't even any exceptions here. Why is it getting less and less and less? So the trend is ionization energy decreases. Well, what's the big thing that's changing as we go from top to bottom? Well, we had a PEL, 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 we had a PEL. So the valence electrons are getting further and further and further and further and further and further and further away from the nucleus. So the attractive force is getting less and less and less and less and less and less and less. If that attractive force is less, it takes less and less and less and less and less amount of energy. Okay, so the distance, the valence electrons are from the nucleus increases, which decreases the attractive force, which means it needs less energy to remove the electron. So going top to bottom is really easy. All right, so that's where we're going to stop for today. We'll pick up with the trends next lecture. All right, have a good day, and we'll talk to you soon.